So as I said, this equation xz equals y squared is my favorite plane conic. The argument I gave you in the previous lecture says that this is a normal form. So given a curve which is a non-empty and non-degenerate conic, then over any field, and this works even if characteristic is 2, although the proof I gave doesn't, then you can always write it in this form. So I want to expand on this idea and work some more with this curve. So that's one aspect of this. Then we're going to see that this curve is actually isomorphic in a sense which I will expand on later in the lecture course. This curve is isomorphic to P1 over K. So I spent most of the last lecture discussing projective space in general, but this projective plane, P2 in particular. So remember, this is my picture of the plane with its three coordinate axes, x equals 0, y equals 0, z equals 0. So this guy is, presumably simpler. And so I want to say let's just go back to the definition. This is the set of ratios x to y. Let me write u to v. Right. So this is so exactly as in the last lecture, when the definition for usual projective space, one of ratio, saying ratio means that one of u v is non-zero, and that u over v or v over u is the only thing we care about. Right? So we don't notice the actual values of u and v, we only notice the ratios. We only notice u and v up to the equivalence relation that I said. So the equivalence relation is multiply u and v by a common non-zero scalar, and that means that we're not interested in u and v themselves, but on the other hand, this expression here, u and v or v and u, is a well-formed expression as long as, in this case, v is not 0, here u is not 0. So this map, I'll discuss this map in a short while, but the map is just given by uv, maps to u squared, uv, v squared. Right? So this is defining a map here. I've got a pair uv, but defined only up to this equivalence relation. I take these and I map them forwards. I send uv into this thing here, which is just a list of all quadratic monomials in the two variables u and v. And lo and behold, if I call this one x and this one y and this one z, then it so happens that xz equals y squared. Right? That product of those two is the middle one squared. Okay? And then there's a business about how we go back, and I'll talk about that in just a while. Meanwhile, I want to sort of give some interpretation of what these things are. So this, when we write down this P1k, or any algebraic variety for that matter, this is a set of points, and it's supposed to have some kind of characteristic notion of function on it. So as you all know, if those of you who've suffered some time trying to read Hartshorne will know you write down x ox and there's a topological space and a sheaf of functions on it, and it's all very complicated. So this thing u over v looks like a function on P1k. So u over v is a, well, what's the word? It's a function, but it's not defined everywhere. It's a partially defined function. On P1. Right? Namely, if v is not equal to 0, then u over v is a perfectly good function. Or more generally, if f is a polynomial, then f of u over v is a function. So the thing I'm driving at here is that I've got this variety P1k. So here I'm just describing it as a set, and now I'm telling you inside there is the piece So this will be an affine open piece, but for the moment just let me write piece. This is the bit of the space with v not equal to 0. Right, and this is isomorphic to k with, so this is, we're going to write A1 for the affine line over k with parameter x equals u over v. Right? So this is exactly the same trick as I used earlier. So this is the same as x to y to z with z not equal to 0 is the same as, is that you can just map this to x over z, y over z, 1, and forget the 1. Right? So I mean, this is really now a very simple thing. I'm thinking of here writing a one-dimensional line here, which is just k with parameter x. So this is just the x line. Right? And then the x, of course, takes the value 0, and it takes, every other value in k, and, the idea of writing down the projective line rather than the affine line is that we have in mind that this x can also take the value infinity. So infinity is a point of P1k. Right? So right, you will find lots of places in the mathematical literature where grown-up mathematicians write x equals infinity, the point where x equals infinity. And you have to understand this does not make sense. You're not allowed to write u over v when v is 0 and say that that's equal to infinity. You can't make deductions based on dividing by 0. Right? But in this case, there is a this idea does have a perfectly good interpretation. I mean, it's an interpretation. This saying x equals infinity does not itself mean anything, but it's just when it's used in the literature, it's a kind of shorthand for explaining this. So you know, people in ordinary speech, in ordinary language, people say infinity, and you know, basically it doesn't really have to have any meaning. Mathematicians have to be a little bit more careful about it. In this case, so in projective geometry, in this case we're talking about the line, one-dimensional line, and it has a single point at infinity. So let me just try and remind you of incomplex analysis. So in this case, we write down this picture here, which is, you know, z equals x plus iy, the complex plane, right, or the Argand plane. So you prove theorems, for example. It's a theorem that if f is a function on if f is a holomorphic function. So holomorphic is regular or analytic I'm sure that you study this in the second or third year complex analysis course. So it means differentiable as a function of the real variable. So the picture I'm drawing here is C. Regular analytic function on C, and if you assume that the order of growth of f is less than the order of growth of z to the power of d, as let me write a constant times c to the d, that's for some fixed d, then f is a polynomial in z of degree less than or equal to d. Okay, so you know, how do you sort of think about these problems? So you know, if for example, if d is equal to 0 here, then f is a function on the complex plane. It's holomorphic everywhere, and it's bounded. So then there's a thing called Liouville's theorem saying that then it's a constant. Right? And the general case is basically not much harder. You open a textbook on complex analysis and you will find this proved. So in complex analysis, what you do is you talk about a disk of radius r here, and I'm going to just let r get very, very big, and then I'm going to take on the complement of a disk of radius some large r, take w is 1 over z as a parameter, as a complex parameter. Okay, so then you get, you know, think of this r as being very, very large. You know, it's gone way beyond the blackboard. It's covering the whole of the universe. but it's not going quite out to infinity, right? And then there is the outside of the disk, and the outside of the disk is some little topological space, and this argument here is saying if we do a kind of reflection and reversing the and reflection followed by complex conjugation, that's what this is doing, then it takes the outside of the disk. So this map here takes the outside of a disk to a little disk with a single point removed. So this single point is the point w equals 0. Right, and outside w equals 0, this map is reversible. This map is invertible. It's just an isomorphism of everything outside the disk with everything here inside this disk except for the single point. Right? And then, if you do the kind of things you do in Cauchy's integral theorem and so on, you can take this f and write him as a function here and investigate, write that integral expression for f, and you'll find that f is now meromorphic in W. So this condition here, so f is regular at every point of the complex plane. Furthermore, at infinity it has this, it's allowed to grow, it's allowed to go to infinity, it's allowed to go to infinity with power d, but no more than power d. So then, as a function of W, you discover that f is meromorphic So meromorphic is Yuri shown. Not sure. I know it from, I know it. So, the words that you use in Korean, some of them come from Chinese, and this one comes from Japanese. So the Japanese were pretty clever at learning Western tricks in the 19th century, and a lot of this sort of scientific terminology comes from the Japanese. Anyway, f is a meromorphic function of W with pole of order less than or equal to d. Okay, so I can translate this condition here, which is just saying the absolute value of growth of f is less than d. That translates into this condition that f has a Laurent series expansion with poles only going up to d. And this means that this implies that f is polynomial in Z of degree less than or equal to d. Okay, so if you ask how many functions are there on, I take this variety P1k, and I have in mind that k is, for example, the complex numbers. I ask how many functions there are, then if you say you want the functions to be regular everywhere, you're perfectly welcome to say that, and the answer is that you only get the constant functions. That's Liouville's theorem. If you ask regular everywhere, then it means in particular bounded at infinity. It means that d is 0 here, and you get a polynomial. You get a polynomial of degree 0, which is a constant function. Right? So you're going to eventually allow meromorphic functions, allowing functions with poles. So you're used to doing this in complex analysis. It's sort of basically a harmless enough thing, and in particular, on P1, I can take this nice open affine piece here, which is just the affine line with parameter this x, u over v, And I can just identify this with A1k, and if you ask me how many functions there are on this, well, you know, if you're an algebraist, you say, well, I like polynomial functions, and you take all the polynomial functions you like on here, and they are now functions on P1, not functions everywhere, functions with poles at the point at infinity, at the single point where v equals 0. Right? So you get this, this picture of, so I can do exactly the same, of course. I can do exactly the same. The same with u not equal to 0. And then I have v over u. Right, so what we're finding is that P1k is the union. It's a union of two pieces. So it's A1k with this parameter x, which is you know, u over v, union another copy of A1k, which is with parameter y, which is v over u. And you know, how these two related. What does this gluing mean? Well, it means that if I've got this x here, and I'm not at this particularly unlucky point where x is 0, then I can just invert x and I get y. Right, so x is y inverse, so no special surprise about this, and it makes sense as long as x is not 0 and y is not 0. So there's a kind of picture that you draw here. It's never, if you draw it over the reals, it's never completely successful. I'm sort of thinking of drawing this A1 there, this is the x line, and then the y line like this. Right, and they're glued together here. It's the same manifold, but just at this one point here, the gluing doesn't work, and at this one point up here, the gluing doesn't work. So on this sheet, right, I take x as a parameter, and x is a nice parameter at this point here. It just happens to be 0. On the other sheet, y is a nice parameter. It just happens to be 0 there. Right. So over the complexes, you do the same thing, and you get P1c is the Riemann sphere. So this, if you think of this just as a topological space, then it is, the complex numbers is just the xy plane, it's just R2. But we make this special arrangement that outside a very big disk, we think of that as a neighborhood of a single point. So this is not the projective plane over the reals. This is not the projective plane in x and y. We don't distinguish the points at infinity going out in different directions. We just think of outside this very big ball as being a single point. So in abstract topology, this is called the one-point compactification. I just take one point out there and I just let it be a neighborhood, let its neighborhoods be, you know, everything very big. Every unbounded set is a neighborhood of that. I didn't say that right. The complement of any bounded set is a neighborhood of that point. That defines the topology on the space, the one-point compactification. So, you know, you do this picture of the sphere, the ordinary round sphere, and then there's a kind of sort of, I don't know, projection. You can do a stereographic projection to say that the sphere minus this point, is just the plane, and then you can do it the same from the bottom upwards, and then you can identify what happened at the bottom with what happened at the top as being Euclidean inversion in the ordinary line, followed by complex conjugation. So that's what this in complex analysis people like to use the letter Z for the complex coordinate here, and the letter W for the complex coordinate at infinity. But it's exactly the same construction. Okay? So this is our idea for functions on P1, K. How am I going to form functions on P1K? Well, we must allow poles somewhere. Right? If I demand that the function is a polynomial function of u over v and also a polynomial function of v over u, then I get the constant functions, which are absolutely beautiful regular functions and so on, but just don't contain very much information. So we must allow poles somewhere. And what happens here is really very pretty. What I say is I'm going to use, so let me write fd over gd, where f of uv, gd is gd of uv, are both homogeneous of degree degree d, the same degree. And I want to insist that the g is not identically 0, right? Because in algebra it's a taboo to divide by 0. Okay, so what am I doing here? So let me say I've got this ring K of u and v. Right, so the difficulty for us is that these are not, so an element there, if I take an element, say f in there, of degree, if I take an element f is not a function on P1. It is a function on this K2 minus 0, which lies over P1K. Right? So I explained, I've got this ratios u to v there. I've got these ratios u to v, and a point of P1K can be written as a pair u comma v, but only up to an equivalence relation. And if I take this function and apply it to u and v, the answer strictly depends on the choice of the equivalence class. So it's not a function here, it's a function up here, and it's not compatible with a projection there. Right? So f, let me go to another blackboard. F of uv is homogeneous of degree d if and only if f of lambda u lambda v is lambda to the power of d f of uv. Okay, so homogeneous of degree d means that it means that, for example, u to the power of d, or u to the power of d minus 1 times v, or u to the power of d minus 2 times v squared, and so on. You can fill it in yourself. U v to the d minus 1, v to the d. Okay, to be homogeneous of degree d means that you're a linear combination of these guys. And if you substitute lambda u lambda v here, then you're multiplying by lambda to a total power of, so each of these, each monomial goes to lambda to the d times itself. So the implication that way is obvious, it's just this calculation. The implication the other way, it works when the field K is infinite. So assume K is an infinite field. Right. So those of you who at some time in the future do a course on Galois theory will learn that there are also finite fields and that might be interested in those. But so, I mean, this is sort of, I don't know, basically obvious. So infinite field means there are infinitely many different possible values for this lambda to put here. So I got a number and another number, and you know, if I have infinitely many zeros, look, I don't know, the proof's easy. Okay, so this means that if I take this guy FD divided by GD as a function of UV defined wherever G of D of UV is non-zero, then it only depends on the ratio U to V in P1. Yes? So I'm not allowed to write GD of UV as a function of a point in P1, because if I do this, it depends strictly on which choice I've made for U and V. Right? It depends by this factor lambda to the D. However, if I do this ratio here of two different guys, this quotient of two different guys, then when I change the representative of the point UV, then this guy gets multiplied by lambda to the D, this guy gets multiplied by the lambda D, so the fraction as a whole is invariant. Yeah, so I've constructed things that are invariant functions partially defined. So I had partially defined earlier. Yes? So I'm doing this in this basically rather easy case now, but this is fundamental to constructing regular functions and the structure sheaf and whatever else you want to do on a projective variety. Right. So the conclusion of that is